what happens when we change the temperature of an object? Well, usually what happens is we have some change in volume. Now, obviously, if we think to the ideal gas law, that change in volume is pretty obvious. PV equals nRT tells us that the volume of a gas kept at constant pressure will change proportional to the absolute temperature. So if we go from 200 degrees Kelvin to 300 degrees Kelvin, we would expect an increase in volume of about 3/2. Okay? For solids and liquids, the amount of change in volume isn't quite as dramatic. Basically, because these molecules are all attached to one another, increasing the temperature, which increases the average kinetic energy, doesn't necessarily give you a proportional amount of expansion, but they do have some expansion. If we think about a solid or a liquid, and we see how the molecules are set up, let's say looking at a solid. As we increase the kinetic energy, what's actually happening here is these individual molecules are vibrating back and forth with some amplitude. The more amplitude that they have, the more distance that they're going to create between their neighbors. So when the molecules are cold and the amount of vibrations aren't all that great, we would expect a minimum amount of distance between the molecules and therefore a minimum amount of volume. As we increase the temperature, the amplitude is getting greater and greater, and the volume should also increase. But again, it doesn't necessarily increase at the same rate that we see with the gases. Now, linear thermal expansion is saying that the change in length of an object, okay, so there's delta L right there, okay, is going to be proportional to some change in temperature, okay? The more traditional way to actually write this is that delta L, can't get my pen to work, delta L is equal to whatever the original length is of an object. Obviously, the longer the object, the more it's going to expand because you have more molecules or atoms next to one another to increase their average spacing, times alpha, which is some coefficient usually related to the hardness of the material. Harder objects don't expand as much as softer objects. You have weaker bonds. So the weaker the bonds, the greater alpha is going to be. And then times delta T, which is the change in temperature. So as we heat things up, they will expand. Now, looking at some of these different objects, we can look to the left-hand side and see the thermal expansion for different metals. Aluminum is a relatively soft metal, although it's light and very strong for its mass. The bonds between the different metallic ions is not as strong as, let's say, copper, or as in the case of steel. So, as we said before, we would expect a larger coefficient of thermal expansion. Okay, here's a special alloy of steel. It's a very, very tough alloy of steel. And it is notable because it has almost no thermal expansion or very little thermal expansion for any change in temperature. All right. What else is interesting to look at right here? Well, you probably, well, let me change here. You probably don't want to pour boiling water into glass. Glass is a very brittle material, and if we create too much internal stress, it will actually shatter. However, Corning was able to figure out a specific type of glass that has a low thermal coefficient expansion and can actually be used to hold very hot water or even cook in. The thermal shock to this glass doesn't create as much expansion. You still can get this glass to shatter. With a much lower thermal coefficient, it is able to take rapid changes in temperature much faster. So again, everything will expand generally when heated. Water is actually an exception that we're going to look at this rule. But whenever we engineer materials, we have to be very, very careful that when they expand, they don't create internal stresses that can actually damage or destroy the material. Now, as you can see here, this is a concrete road surface, probably on a bridge someplace. You can see the concrete on the left and the right-hand side, okay? This between it is what's called an alligator joint. This allows the bridge to expand, okay? Actually, contract when it's cold. The alligator hinge will actually open up. And when it's very warm out, the concrete will expand and push this joint together. So these expansion joints are very, very critical for many structures because they allow the structure to expand when it's hot and contract when it's cold. Here you can see a expansion joint. This is some type of elastic material, some type of polymer, and we can see this concrete block wall, which has this little joint in here because on a hot day, the concrete will expand. On a cold day, the concrete will contract. And this little joint allows it to do that. You'll even see this on a sidewalk. You know, no sidewalk is poured as one complete slab. Actually, pour it as individual squares, and then between the squares, create the expansion joints. So where are some examples where we have to be considerate of the expansion properties of a material? Well, looking at metal framed windows, we'll typically use rubber gaskets, not only to keep things sealed, but also allow the metal and the glass to expand at unequal rates. Metal hot water heating pipes should not be used in long straight lengths because they will expand or contract. And you can actually hear this sometimes in houses. When the hot water is going through the baseboard, you'll actually hear the expansion take place, and it sounds like knocking. As we said, large structures such as railways, bridges, they need expansion joints to prevent damage. Railway lines actually, the railway irons actually used to bend and create what are called sun kinks, create sun kinks in them during very, very hot days. And of course, thermometers are another good example of thermal expansion. If you simply look at the expansion that a metal undergoes, actually a bimetallic strip, you can use this to actually gauge the temperature. And here you can see some kinks that were created. In fairness, they can be created during very, very hot days. These were actually created by a seismic event because we don't use the type of metal, we use low expansion steel in rails today to prevent this from happening. So, I cheated a little bit. I used a picture from a seismic event. But again, you can see in this bridge right here, clearly they're using alligator joints, which open and contract, open and close, depending on the temperature of the air. Okay, let's take a look at an example. And this is similar to some of the homework problems similar to perhaps a test problem that you might have. And there's our equation for linear thermal expansion. We say it's linear because the objects that we're talking about here are very long or tall compared to their other dimensions. Okay. And we're trying to see how much longer they will become. Okay. Here's our L0. Here's our delta L. How much longer they're going to become as we change the temperature. So what we're going to use is a very tall object here. We're going to use the Eiffel Tower. And the question is, how much taller is the Eiffel Tower on a day where it's 25 degrees Celsius compared to the coldest day where it's 2 degrees Celsius? In Paris, I guess the temperatures don't change very much. Now we start out with a height of 324 meters, okay? This we'll just take as the height on the coldest day. You could use hottest day or coldest day. The expansion that takes place isn't going to be all that great. So we're going to place that as our L0, okay? We will use, for structural steel, the thermal coefficient of expansion, 12 times 10 to the negative 6, 1 over degrees Celsius. Now, if we're made out of Invar, that would be down to about 0.9 times 10 to the minus 6. And finally, we're going to calculate the change in temperature. Remember, our final temperature is going to be 25 degrees Celsius. Our initial temperature is 2 degrees Celsius. And because this is a delta, we can use degrees Celsius. If it were just a T, like in the ideal gas law, we would have to use Kelvin, but we can use Celsius here. So 25 minus 2 is 23 degrees Celsius. I plug that in right here. Originally, it was 324 meters tall. That's my L0. And there's my alpha, my thermal coefficient of expansion. So we multiply everything together. We get a surprisingly small amount. It only changes length by 0.089 meters. That's 8.9 centimeters, okay? So you look at the Leaning Tower, I'm sorry, I'm saying the Leaning Tower. It's the Eiffel Tower. You look at the Eiffel Tower on a hot day, you look at the Eiffel Tower on a cold day, you're not going to notice a difference in height. However, it is significant enough that if we didn't take into account this thermal expansion, that change in length could actually damage some of the structure if it wasn't allowed to expand. And again, here's an actual sun kink. This actually happened in New Jersey. And you can see where the intense heat heated up the rails to a high enough temperature. They tried to expand. Of course, they couldn't because they were basically set in a straight direction. And it was enough to warp the lines, and this poor car right here actually derailed as a result of that. Again, most rails today use low expansion steel, so this is not as big of a problem. If you ride the trains, you do notice that there's a little bit of a bump, as you're going along the lines. And again, that's because one rail is not set exactly next to another rail. There's a little bit of a gap for expansion. And this is also one of the reasons why the high-speed rail lines are so incredibly expensive to make, because they're one continuous welded line. They have to use extremely expensive steel, like an Invar. And due to the high velocities, you really can't use expansion joints. Here's another application of thermal expansion. This is a bimetallic strip. We know that brass has a higher thermal coefficient of expansion than steel. So if we heat a bimetallic strip, and these are basically two strips of metal that have simply been welded together. If we heat this, the steel will expand a little bit, okay? But what expands more is the brass, okay? Now, the easy something is to stretch the upper surface of it and compress the lower surface. Well, here the brass is expanding more than the steel is. So what happens as a result is we get an overall curvature right here. And this curvature, okay, is going to go in the direction of the less expansive material. So steel expands a little bit, brass is a softer metal. In fact, if you used an even softer metal like aluminum, it would expand even more. So again, we can use this bimetallic strip for a number of different applications. One application is a thermostat, and this is an oversimplification of a thermostat. In reality, if we look at the bimetallic strip, they'll actually wind it in sort of a long helical spring. And this will enhance any slight change in curvature due to the change in temperature. Okay. And instead of just using a simple contact like we see right here, oftentimes what they'll use is a glass tube of mercury metal. And as the mercury changes its orientation, it makes contact with two leads, and that'll turn on or off a furnace or turn on or off a air conditioner. Okay, but you know, this would work too. This is a little more reliable, but there's a really good application. This is the actual coiled up bimetallic strip, okay? And here is one of those mercury switches, which turns it on and off. And this is a very popular and inexpensive thermostat made by Honeywell. I don't know if you can still buy them, but very, very simple. Also very, very reliable. Of course, we don't like using mercury a lot because of its toxicity. Okay, so linear expansion, this equation works very, very well as long as the temperature changes aren't very extreme, okay? And again, this alpha really depends on the material. More precisely, alpha tends to be larger for softer materials where the bonds are weaker. Weaker bonds mean that the bonds can actually expand more for a given amount of temperature. And as the material tends to be harder, the bonds being stronger, alpha is not quite as large. Now, what about the area? Okay, what we started out with is we started out with an object that was very long, okay, compared to its other dimensions, okay? Therefore, all we were interested in is how much longer it got, because how much it changed in the other dimensions really wasn't all that significant. Now, instead, if we have an area of some material, okay, some area, we know that it's going to expand to increase that area, where this new added area is going to be delta A. It's going to expand in this direction, it's going to expand in this direction. And that extra length that it gets here and extra length that it gets here, that is going to correspond to an increase in area. Now, I can convince you geometrically, okay? Let me draw this as precisely as possible. I can convince you geometrically that if this is my area right here, okay, and now I'm going to add extra length in this direction. I'm going to start out with a square. And extra length in this direction. Okay? That the extra length is delta L, right? That's that linear thermal expansion, okay? And there'll be a little bit of area here, but that's going to be insignificant. All right? The extra area that we get, right? The extra area that we get is going to be equal to 2 times delta L, okay, times the original length. So that means that if I come up with an area coefficient of expansion, and actually you got to be a little bit careful here because you know, this area is times the original A or the original L. This time is times the original L. But in any case, geometrically, I was trying to show you that the area coefficient of expansion is approximately equal to twice the linear coefficient of expansion. So what you get is this. The extra area as we heat something up is equal to this gamma times the original area times delta T. Okay? We can also show this mathematically. Okay? Here's our equation we just saw right here. Okay? I'm going to show you that gamma is actually equal to twice alpha. Now, the area that we gain, if this original area is sum square L0 by L0, the total area is L0 squared. All right? So what I'm going to do now is say, all right, okay? The new total area is going to be my original length plus the delta L that I'm going to gain to the second power. Length times width, but it was a square, so length and width are the same. It's just length times length. Now, if I square this, I get 3 terms. I get the original area, I get this new term right here, and I get this term that's really so small, it can be ignored. Okay? Remember the Eiffel Tower? It's 300 and some meters tall, but only changed by 8 centimeters. Okay? That small fraction squared is even smaller. So generally, we can just ignore this, and my new area becomes the original area plus this term right here. Okay? So my area is equal to the original area plus delta A. This is my delta A right here. What did we say delta A was? Delta A was equal to the original area. Okay? Oops. I got my coefficient. Gamma times the original area times delta T. So that's this term right here. All right? And here we see that this term is 2 alpha. This 2 alpha is going to replace this gamma right here. And that is the final equation that I wanted anyway. Okay? So again, it shows that gamma, which is the area coefficient for linear expansion, thermal expansion, is equal to twice what alpha is. You can do the same for volume, okay? The change in volume of anything is equal to this volume constant of thermal expansion, where we have the original volume times the change in temperature. And again, you can go through the math for that too and show that the volumetric expansion coefficient is 3 times alpha. Okay, that's where you start with the cube. All sides of the cube are equal to L0 initially. Okay, and as it expands, we get extra volume. Okay, here's some different thermal coefficients. And we can see here is, once again, lead, a fairly soft metal. So it's going to expand quite a bit. Here's aluminum, slightly harder, doesn't expand as much. Brass, harder metal. Remember iron or steel, less than brass, okay? And again, we don't have INVAR here. Yeah, as I said before, more applications of thermal expansion. Pyrex glass is a low expansion glass. So thermal stresses are smaller than for ordinary glass. Again, you don't want to try this experiment at home, but you wouldn't want to boil water in a normal glass in your microwave. Not only is that not a great idea, because the glass gets hot with a hot liquid in it, conducts the heat very, very well. You're going to produce thermal stresses that will probably shatter the glass. Pyrex, however, doesn't have that. You know, one thing people don't realize that as the Earth is getting warmer, 90% of the thermal energy actually ends up in the ocean. And you think, oh, the ocean gets warmer, the ice caps melt, and that's why sea levels go up. It's part of the reason why sea levels go up. But about half the contribution, maybe a little bit more than half, actually comes from the fact that by heating the water in the ocean, it will thermally expand, or it'll expand due to thermal expansion. So as we make our planet warmer, sea levels are going up as a consequence of ice caps melting in Greenland, in Antarctica, but also because just simply heating up the oceans are going to make it occupy more volume. Now, water has a bizarre behavior near its freezing point. Believe it or not, water is the most dense at 4 degrees Celsius, okay? And if you actually cool it further than that, its density will begin to drop. Now, we can understand this because as we approach the freezing point of water, the water is beginning to stick to one molecule to another, and it's almost beginning to form the precursors of macroscopic ice crystals, okay? The temperature is still too high. So on a microscopic scale, it's starting to link up and form these hexagonal crystals with a large space in between. So right before it freezes from 0 degrees Celsius to 4 degrees Celsius, it will actually expand as it cools down, okay? So very bizarre behavior from water. Again, it has to do with the fact that water is a polar molecule with oxygen and 2 hydrogen, the hydrogen being positive. And that when it links together, it forms these hexagonal crystals. Again, not very efficient in terms of taking up space. And what that does is reduces the density, okay? Now, ice is about 90% the density of liquid water, okay? Here, you take a look at 4 degrees, our density is 1 gram per cubic centimeter, and at 0 degrees, it's 0.9999, okay? Not the 0.90 that we know ice is when it freezes. So the effect isn't huge, okay? It's like, I don't know, 1,000 times weaker than the expansion that happens when it freezes, but it is measurable. It's one of the reasons why during the coldest months in a lake, fish will actually go to the bottom because that's where it's warmest, okay? Near the surface where the water is freezing, the water is actually at 0 degrees Celsius. Now, think about this. At 4 degrees, the water is at its densest, okay? So 4-degree water is going to settle at the bottom here. Whereas at 0 degrees, it's going to stay near the surface of the water. That creates a real stratification in the lake, okay, in terms of temperature, thermal stratification. So this ice gets thicker and thicker and thicker and thicker, but it's always 4 degrees down here, okay? So again, although the fish are pretty much hibernating and not really doing much at 4 degrees, their metabolism is slowed down. It's easy for them to survive that.